Hello everyone, welcome to our presentations. I'm going to present our new directed fuzzing work, which is Everything is Good for Something, Counterexample Guided Directed Fuzzing. This is a joint work with City University of Hong Kong, Hong Kong University of Science and Technology, as well as EPFL. So let's start. So as software plays a key role in every aspect of society, software bugs are prevalent and can cause severe consequences nowadays. They can not only influence worldwide facilities and devices, but also threaten human life and finance. However, software is becoming very large and evolving rapidly nowadays. For example, the rapid growing codebase of daily use software such as Linux and Chrome browsers is extremely large with over 10 million lines of code. The code size of software relying on hardware such as Tesla is even larger, with more than 100 million lines of code. The height for the print paper containing the printed code of Chrome can be more than 370 meters. Therefore, detecting vulnerabilities in such large software is like finding a needle in a haystack. The explosive paths and their complex path conditions introduced by such complex code size make detecting vulnerabilities in real-world scenario extremely challenging. For example, the Neutrous vulnerability, Heartbleed, involves more than 13,000 lines of code across 7 files. Even though this huge code size makes it difficult to detect, it only accounts for a minority of the whole project, whose size is over 1.5 million lines of code. Moreover, generating input to satisfy the path condition is also an NP hard problem. To detect and fix bugs more efficiently, directed fuzzing is proposed and aims to detect specific bugs automatically. It has various applicable scenarios such as patch verification, one-day POC generation, and debugging. The success of directed fuzzing is inherited from the conventional fuzzing, which is lightweight and easy to deploy in various application scenarios. Basically, it leverages lightweight input generation methods such as random mutation to efficiently produce lots of test cases for examining the target programs. It will report the bugs triggered to the developer directly. Meanwhile, if the test case triggers new program behaviors, for example, detecting new coverage, then this input will be preserved as the seed template for further input generation. Overall, this feedback mechanism allows fuzzing to gradually explore the whole programs. On top of this, directed fuzzing uses additional execution feedback to adjust the priority of the preserved inputs uniquely for the targets. The key intuition of existing work is to prioritize paths closer to the targets. Closeness represents the possibilities of reaching the target. For example, the existing directed fuzzing will prioritize path 1 over path 2 since in terms of the control flow distance shown in this example, path 1 is much closer to the target at block E than path 2, and therefore prioritizing path 1 can make fuzzing more likely to reach the targets. However, even with those prioritizations, the majority of the inputs are still randomly generated. We observe that one of the main problems caused by this mechanism is the deficient bug triggering. Especially, directed fuzzing could spend much more time to trigger the bugs after reaching it. For example, in our evaluation of Magma using AFLGO, triggering the targets can be 1,000 times longer than reaching it. The root cause of such issue is that the majority of the inputs cannot even reach the targets. In the previous evaluation, we observe that nearly 100% of the generated input cannot even reach the target program points where the bugs occurs. We also apply state-of-art pruning techniques, for example, beacon, to terminate executing these inputs, which over 80% of these invisible inputs can be pruned. Nevertheless, the majority of the time is still wasted on executing these invisible inputs. For example, executing the invisible inputs from the previous evaluation, so even with the filtration techniques, still accounts for over 88% of the fuzzing time. Therefore, we summarize this problem as an indirect input generation problem. Especially since most existing work only focus on seed prioritization with different feedbacks, they overlook the input generation, which is not directed to targets. In this paper, we present a novel solution named as Counterexample Guided Directed Fuzzing to tackle this problem. Our tool, Halo, can generate 6.2 times more test cases than the state-of-art directed fuzzing to reach the targets. With a higher ratio of the reachable inputs, we achieve a 15.3 times speedup to detect the same bugs. Moreover, such efficiency improvement also enable us to detect 10 incomplete fixes of the previous CVE or bugs. The main challenge we're facing is that if we attempt to direct generate input reaching the targets, then fuzzing needs to solve the path condition, which then suffers from a numerous path explosion and expensive constraint solving problems. Therefore, our intuition is to leverage such a large proportion of the unreachable inputs to guide subsequent input generation. Specifically, we transform the problem as, with a given input satisfying certain patterns, especially we regarded as path conditions, can we generate more similar or contradicting inputs following the same patterns? Therefore, we can increase the frequency of input reachable to the targets. Our key insight here is to approximate the condition efficiently using existing fuzzy inputs and outputs to improve further input generation. Specifically, we approximate the condition based on existing input so that the new input generation only focus on generating reachable ones. Therefore, we can have a higher probability of triggering the targets. The iteration process of fuzzing also helps us to adeptly refine the precision of the approximated condition. To efficiently approximate the condition, we use a lightweight dynamic likely invariant inference technique. Specifically, we initialize our approximation with some executed input. Since it is not precise, we refine our approximation with newly executed input. Meanwhile, the invisible inputs are also helpful as they can reduce the over-approximation of our invariant. Invariant infer can serve as a boundary for input generation for each input byte. We then only sample the input from the constrained search space described by the invariant, which is more likely to satisfy the path condition. For example, with a precise approximated condition, we can know that the first 4 bytes should have the fixed value so that the variables x influenced by this byte can always be 10 and satisfy the condition to the target at line 3. Specifically, we summarize the 2 challenges needed to tackle for achieving our insight. First, one is how to efficiently infer the condition from the executed input, and the second is how to generate input constrained by the condition efficiently. Still, the scalability of approximating the condition is the root cause of solving the challenges. So we interpret such challenges from three aspects: relevant input bytes and their values with the relations. The preliminary steps is to infer the invariant, is to identifying the relevant input bytes, since invariant inference is not scaled for large input size. Therefore, we adapt the time inference approach to determine the related bytes. Specifically, we regard bytes as relevant if they influence the variable values in the branch condition reachable to the targets. For example, by sequentially mutating each byte, we can observe byte 1 is relevant since the value of byte 1 influences the value of x at line 3, which is reachable to the targets at line 6. Therefore, we will infer the invariant for this relevant bytes. With the relevant bytes, we then address the challenge 1, which focuses on obtaining the related values of the target condition. The exact problem we need to tackle for challenge 1 is how many inputs are needed to approximate the condition. Our intuition here is that not all inputs contribute equally to approximating the conditions. More specifically, only the condition near the boundaries help. For example, to approximate the condition x greater than 10, the above set of input is much closer to the boundary 10, so it is more likely to approximate the precise condition than the size of the input below, because they are far to the boundary, and so that we do not know what is the exact condition that separates these two sets of input. To precisely stack those inputs, we measure the distance of each input towards the boundary. Specifically, we regard each condition as a function whose inputs are the related variables. In the third space of views, inputs that makes the output of this function to be 0 consists of the boundary. The distance can be regarded as the closeness to the input, making the output 0. Therefore, we use the absolute value of this function collected during the execution to measure the distance. For example, by calculating the absolute value, we can notice the above sets of input have similar smaller distance to the boundary than the below set of input, and thus should have a better precision when approximating the condition. We then calculate the sample size based on the statistic to satisfy the confidence interval where the alpha is bigger than 0.95. By selecting the useful inputs, we can efficiently approximate the condition with the invariant. Next, we're going to effectively generate an input, which needs to tackle the precision of the relation. To maximize the usabilities, conventional invariant inference provides diverse invariants for users. However, it is impractical to generate input based on all invariant infer, considering the efficiency. Specifically, input generation speed based on sampling the relations is linear complexity based on the number of invariants provided. On the other hand, since invariant can have different precision, we thus need to select the most precise invariant for further input generation. For example, we show 3 kinds of common forms of the invariant inferred here. We can find that the interval invariant is less precise than the polyhedral invariant, while generating inputs from the polyhedral invariant is much more expensive than the interval invariant, which we only need to do random sampling. Our solution to tackle this challenge is importance sampling, in which the importance is adaptively adjusted according to the fuzzing process. The importance represents the likelihood of selecting this invariant. In particular, we assign an initial importance for each invariant inferred. Then, its importance is adjusted based on the success rate of generating reachable input. For example, for invariant x greater than 5 approximating the original condition, we decrease its importance whenever the counterexample is generated, and vice versa. Eventually, the more precise invariant will be preserved. If no invariant has sufficient precision, we invoke the invariant inference engine again to refine the invariant inference. By leveraging the dynamic invariant inference technique, we also can effectively leverage the execution feedbacks to directly generate input towards the targets. In summary, by leveraging the reachable and unreachable inputs towards the targets, we gradually approximate the path condition reaching the target by a dynamic invariant inference technique. Therefore, we can increase the proportion of the reachable inputs generated and also the probability of triggering the bugs. Thanks for listening.